Hello. So yeah, the topic of the session is about discussing all the improvements that have been done around the load tracking in the scheduler and what we are working on for the next step. So I will start to just describe the problem that we have faced with the scheduler load tracking and mainly the CFS. Which kind of enhancements, and then I will finish with some bench on the Android platform. So yeah, so the problem is that with the pair entity load tracking, which is used in the scheduler, which have been implemented, don't remember, 4 years ago, we haven't been able to get the best performance on some platform like Android phone, and which the main effect is that, we have compared that with the Windows load tracking, which was another implementation done by Qualcomm. And it was clear that we were not able to reach the same performance because of several reasons, like the responsiveness of the load. The load was really slow to increase or stay at a low level, whereas it should not be. We have also discovered that when a task, so C group is used in Android, which and the main effect is that when task was migrating between group, the load was not propagated with the task migration. And also we have discovered also different bug and regression with the tracking of the load and the utilizations. I'm going to go through that. So here is, so this is a simple use case in which we have two tasks running. So task A and task B. It's not really visible, but the color corresponds to a different CPU. So it means that here task B is migrating between two CPU. And below is all the load and the utilization on the CPU. So it's a bit a mess, but we can see some typical wrong behavior. So we have one there that we have already discussed several times, is that the utilization of the load of an idle CPU is stalled, so it keeps at the last active level, which means that if you use the scheduler value, you will see this idle CPU as busy, and this can have an impact in the load balance of tasks. The other one is that when a task here, we have task B, which is a small task running periodically, migrate between two CPU in a C group. What's happened is that the load stay and the utilization stay on the previous CPU, and the new CPU that is used start from 0. So we are increasing. What happened with ScheduleTill is that after a while, ScheduleTill detect that we don't have any load, and decrease the frequency to the lowest OPP, which means that we will slow down before restarting. Another strange behavior is this. I mean, we have stable behavior, but we can see that the load and the utilization is not stable. We have a significant impact. I think it was something like 30%. This was because of some bug in the load tracking mechanism. And the last part here is that, so we are in the same group, so we have two tasks in the same control group. And normally we have to share the load and the priority between all the tasks in this group, so between the CPU. And we can see that even we don't see any huge difference in the load and the share between when we have only one task running or when we have two tasks and one big task, which means that the big task will not have that much priority or running time compared to another group, which make this time execution to be slowed down as well. So based on this status, we have merged more than 20 patches since 4.7. We have some notice. So yeah, I have mentioned probably two main patch. We have noticeable effect on the load tracking, but there are a lot of more. So one is about propagating the load and the utilization between control group in the scheduler. Another one for tracking small tasks. So it has appeared that if your task was running less than a tick, the load may not be accounted correctly. That's why we have this up and down effect. And we have more patch to come in order to solve the problem with the block load of idle CPU, and we're also testing a new way to take into account frequency scaling or micro-architecture scaling in the load tracking. So with all this patch done, we have this new, so we have run the same use case, and we have this new behavior. So the first thing, so it's still the same. We have some task migration here and here. One first thing that we can see is that when the tasks migrate, we can see that the load and the utilization also migrate. And the main effect is that from the frequency scaling point of view, we stay at the same OPP because we see that we have the same utilization. It's the same there. So the tasks start on one CPU, then migrate, and we can see that we have a continued value for the load and the utilization. The other interesting point is that this load is stable. We don't have this wave effect. And the last point is for the control group and the share of the load between the different CPU. So when the big tasks start to run, so at the beginning, so the small task, I've got almost all the load of the group. And then when the big task starts, we can see that the load for task B decrease because we have to share this load with the other task. And at the end, because we are updating the load of block CPU, you can see that once the big task go back to sleep, we are putting back all the load and the runtime to the small task. So that's just to have a comparison. So it's really about that, in which we can see a lot of variation without any good reason compared to this one. So yeah, that's another one for a new frequency scaling invariant scheme, just because we can't see that there. In this one, the goal is just to compare how the utilization and the load of a task can increase, how fast it can increase if you are running at the max capacity, which is the first one there. And we have there the current frequency scaling invariant scheme. And we can see this, so with the current implementation, the utilization is capped by the current capacity of the CPU. So we can see that we are reaching for each OPP, the max value is capped by the current capacity. So we have this limit effect. With the new scheme that we are testing, we don't have anymore this effect, and we are increasing more quickly. So we have here more than 120 milliseconds of difference in responsiveness to reach the max OPP. So that's all the fix we have mainly worked on. And once we have reached this, let's say, once we were satisfied with this unitary test behavior, we have moved to more realistic test. So for that, we have used an Android A key with Android, so the common branch, Android common kernel branch. We have used mainly the Velamo bench and some UI chunk tests, which is the recent Fling, and also the hardware UI tests, which are available with Android, in order to be sure that what we were seeing from a unitary test had an impact on more realistic test. So just one point about thermal mitigation. So when running all these tests, the platform tends to overheat, which impact, so the default thermal mitigation is frequency capping on the I key. So I have tried to see how we can, what was the impact of the thermal mitigation on performance result. And the conclusion is that that's not really simple and straightforward. So I have done some tests with external active cooling just to be sure that the platform will never overheat. So I got some performance result, and then I have just let the board overheating normally. And the results are not always better with active cooling. I mean, sometimes when you are overheating, you can have a better score, which is a bit strange. And in fact, in the Velamo multi-core test, one bench seems to really like overheating. We have something like 20% better score for this particular part when thermal mitigation is activated, which probably means that this test is not really impacted by the frequency scaling, but more by something else. I don't know. I don't have any clue or any conclusion. But for the other score, the result was almost, we have better result when with active cooling, without thermal mitigation. So for the Velamo multi-core bench, I have done 3 tests. So I have used the Android kernel with the default configuration. I have done that on the V4.4. I haven't found time to move to the 4.9, which have been released a few weeks ago now, a few months, maybe 1 month ago. That will be probably the next step to be sure that we still have the same improvement on the latest kernel. So this is the score for the default configuration when we are using the Vault, Windows Entity Load Tracking. This one is with the legacy PELT, so it was the PELT available in V4.4 without any improvement. And this one is with all the improvement that have been done on the load tracking. So I have put standard deviation just to make sure that we have stable result. So as explained, so for the thread bench, we can see that we have a lot of variation. We tend to stabilize the variation, but yeah, it's still significant. So what's happened is that from an overall point of view, we have an improvement, significant one. For some bench, we have almost the same. Whatever. For this, it's look like the scheduling, the load tracking is not really what, I mean, it's probably that we just want to run everything at max. I haven't all the detail of the bench. But for others, so the sys bench, which is mentioned to try to stress some kind of user interaction, parallelism, we can see some improvement, significant one. For thread bench also, we have improvement. So it's a bit more difficult for me to understand that or to explain, just because thermal mitigation have a better impact, a better effect. And also for the process communication. So the conclusion is that we can see in more realistic use case a benefit with all the improvement in the load tracking mechanism, which means that probably most of our issue were there because of bug in the load tracking. And then I have also done some UI interaction bench. So this is for recent fling. And the same, I have both 3 different use cases, the default one, the legacy PELT, and the new one. I have just highlighted this one, but I would say, yeah, we can see some improvement, not that significant improvement, but at least for the, so yeah, maybe I should explain that a bit. The point is that it's the average value in order to have 50% of all the frame that have been rendered in less than that, if I'm not wrong. And here is the average value to have 99% of all the frame rendered in shorter time than this. So we can see that with the legacy PELT we have a significant regression, and we can see some improvement compared to Vault. So that's a good thing for us. Especially that means that we can, the goal for us is really that to be sure that the main line is at the right level to be used by default instead of using some custom implementation.
performance improvements, you don't know if you're trading off power to get those.
I haven't done any power consumption measurement. But I would say that for the Velamo bench, I'm not sure, so yeah, no, I haven't done any performance. The main issue is that thermal have a huge effect in this bench. So I'm not sure that the best bench to look for power consumption for the Velamo bench, for example. Is it really what we are looking for with the Velamo bench, or do we are more interested by the performance? Because, yeah.
I mean, we normally normalize our per watt.
Okay.
I mean, how do you trade that off? Sometimes you want the performance.
Yeah.
So performance efficiency then.
Okay. Yeah. So yeah, the next step would probably to do some performance, some power consumption measurement just to check.
And maybe can comment because basically Andres did the backport of some pieces on the pixel baseline and yeah, so there has been this backport of some fixes on the 318 pixel baselines, and we actually did some initial experiments with that, and currently we don't see any big regressions, let's say.
It is slightly different, but it's not massively different in either direction, and it varies what's better and what's worse.
Yeah. And that's both performance and power.
Yeah.
That's it.
Okay, I might bug you guys later to share some of the data.
Yeah, we are actually, Chris presented some of that yesterday, but yeah, we can, yeah.
Vincent, when you say thermal mitigation, is it dropping to the lowest OPP or you jump to one level lower?
So on the high key, there is two tipping points. So at 3 points at 65 degree, I think we are disabled the highest, and at 75, we have another step. I don't know exactly which point is it, but yeah, it's not directly to the lowest.
So would you call the new PELT, is the C group fixes and the new matrix for the ramp-up, or just the C group fixes?
No, the C group fixes, small task fixes. There is the new scale invariance. I have put all the yeah.
Do you have put results without the new scale invariance or the fixes?
No, I haven't. That is, yeah. Yes, probably. Just that maybe once we will have our farm available, we can run a lot of tests. But it takes a lot of time running.
Yeah.
What's the status of the scale invariant stuff? Is it on the list or not ready yet?
So, no, it's not ready. It's not on the list yet. I'm still, the goal was to do a lot of, some unitary tests are nice now, and the goal was to do more functional tests before. So what next? So right now, all the load tracking that we are speaking about are for CFS task, fair task, which is only one part of the load tracking and the scheduling. I will not speak about deadline scheduler because Yuri will speak about that better than me. I think it's tomorrow. The last one is the RT task and the utilization tracking of RT task. I'm going to speak about that a bit later. And the other one is how to improve responsiveness furthermore. I mean, even with the new scale invariants, we can see some responsiveness improvement, but we are not that fast. I mean, we can't really detect 2 5 millisecond task. It's really too short. So how do we improve responsiveness for this task? That's some question that we have already discussed several times. Maybe now we start to have some answer, like deadline, the schedule way to cap the mean capacity. Instead of trying to really track the load of this, maybe you can just tag them.
The schedule tune-based approach is use case tuning.
Yeah.
So it's not relying on the scheduler to detect that. It's
Yeah.
Hinting user space
Exactly.
to boost on necessary.
Exactly.
I mean, it doesn't sound like there's any, I guess, solid ideas yet on how to further improve the responsiveness. I think the Windows system will respond within 2 windows.
No, yeah, but the point is that
other ways to solve the problem, maybe. Right?
Yeah, my point is that we speak a lot about these small 5 millisecond long tasks which are involving UI interaction and where we want to respond fast. But how about all the other small tasks which are involved in use case which doesn't need to react fast? I mean, it's really, for me, right now I haven't been able to find a good description how to describe this task that we want to react fast compared to the other one. And I'm not sure that we can automatically detect them. It's really use case dependent, in my opinion.
Yeah, and well, personally, I think the tuning aspect is kind of orthogonal because we still need the tuning. I mean, the schedule. We also be using Volt, so there is still this user space, kernel space.
There's always some of that, but I mean,
Yeah.
the responsiveness with the Windows tracker is much quicker still.
Yeah, I agree that the Windows load tracker right now is much more responsive for 5 millisecond task. My point is that do we really need to detect this small task for the CFS scheduler? With load tracking, can't we use another way to detect that instead? Like using C group and, let's say, tagging some task or group of tasks as being user interaction task, we need responsiveness, and just say, instead of trying to say, okay, after 2 milliseconds I'm able to detect this task and increase OPP, we can just start by increasing the OPP when they wake up. So for tracking the utilization of RT task, so right now with the mainline implementation in Schedutil, RT tasks run at max frequency, or at least it tries. Because for example, on iKey, we need something like 1 and 1.5 milliseconds to change the frequency. So if you have a 2 millisecond task, it will not run at max frec. And furthermore, we need a RT thread to change the frequency. So we can imagine that we can compete with the RT thread just to change the frequency for this thread. So at the end, I'm not sure that we are really able to run at max freq for small RT thread, which are what really need this max frequency. In the mainline, we also have the RT average, which is the only load tracking of real-time task. It's used in order to estimate how much capacity is used by RT thread, but from a long period point of view. So it's really fine for this. But that doesn't work really well if we have if we want to track that in a more dynamic way. We start to have some issue just because how it's done. It means that we can't use it. So one possibility would be to use something similar to what we are doing in CFS, for example, for the RT at run queue level. Not sure, I'm not saying that's the solution. That could be a solution. I'm not fully convinced by that, but it also means that we have the same responsiveness issue than CFS. So yeah, for that maybe we should look at other tools like ScheduTune, MinCap for a group of tasks, something like that, or deadline scheduler. Maybe it's just that mean that this task should move to other kind of scheduling class. So that will be, yeah. That's something we still need to study, to make experiment. And for the per entity load tracking, how to improve the responsiveness, that will be the next step also for us, is that, so I know that I've spent some time studying the windowing the decay, just to be sure that a task will not go back to, a big task will not wake up with a null load or null utilization. Should we change how fast the load is increasing and decreasing? That's something we have already speak about. We don't have any good, I don't have any good conclusion on that. And personally, I'm more and more convinced that maybe we should use other scheduling class than just trying to improve that metric. But I don't have any real clue about that. That's something we need to look. So that's all for this session. We have an hacking session this afternoon, a time hacking session. So it's more, the goal is more to discuss openly about that, to exchange, to compare possible solution. That will be in this room at, no, that will be tomorrow, sorry. Tomorrow at, I don't know. But yes, tomorrow afternoon, we will have a lot of discussion around scheduler. So deadline, PELT, ScheTune. I'm sure I've forgotten some, but yeah. I think we have a few minutes if you have any questions. Or maybe it's already too late.
To look into what happens when we you mentioned, I think, block tasks. So what happens when a task goes to sleep, and when do we go and say the load goes down, and how that interacts with the governor?
So with the frequency, CPU frag governor, you mean?
Well, I mean, say the task goes away,
Yeah.
goes to sleep,
Yeah.
and then the load in PELT stays high,
Yeah.
right? So we need something to happen to keep the load,
Yeah.
and we still don't rely on the tick today.
No, so we have a patch for that, which is we make sure that we try to periodically decay. So we have, in the scheduler, we have a function called update block idle load for all the idle CPU, which is only called when we are doing some load balancing, right? So that's not a, we don't know what this will happen. That can never happen. If you have only one task, we'll never call that. So we have a patch to make sure that this function will be called periodically, not at every millisecond, but in a, let's say, gentle pace, just to be sure that we will decay this load. And that's what we have seen. That's why, for example,
So guarantee that will actually lower the frequency in that case.
sorry?
Guaranteeing that will lower the frequency in that case before going to idle state.
Yeah. So that's why we can see there. In fact, that's what we have a patch for that. Here you can see that. So it's every few dozen of milliseconds, and the main impact is that we can just put more share on tasks which are still running. That's the main impact. The goal is not to, in frequencies, from a frequency scaling point of view, right now after tick, we don't take into account the load of idle CPU from a schedule point of view. So that doesn't change a lot of things. It's more about how to share the runtime between tasks.
So in your experiments, you don't see us going to idle at a higher frequency?
Going to idle at high frequency is not always an issue if you can pour off the cluster. I mean, the OPP in itself is an issue if you are in WFI. In this case, I agree. But if you know that all your CPU and your cluster are going to be idle for a long time, we will pour down the cluster, so the leakage will be almost null, whatever the OPP you have selected. And if you are, oh yeah, I think we are too late. And if we are on WFI, it's probably mean that we want to wake up shortly, so that's not a big issue to say IOPP for a short time. We can discuss that more. Thanks, everybody.